And in the last several years, I was interested in studying mathematically this Isobe-Kakinuma model. This is a model for water waves. And this model was proposed by Japanese researchers, Professor Isobe and Professor Kakinuma. And they are not mathematicians nor physicists. They are working on coastal engineering. And they derived the model, this model by using the variational structure of the water waves. On the other hand, as you know, the water wave problem has a Hamiltonian structure. And as far as I know, the Walter Craig likes very much this Hamiltonian structure for water wave problem. Also, this Isobe-Kakinuma model is derived as Euler-Lagrange equations to some Lagrangian, but its Hamiltonian structure is not so trivial. So therefore, I chose this topic to talk in this workshop dedicated to the memory of Professor Walter Craig. And this talk is based on the joint research with Vincent Duchesne at Université de Rennes in France. Before going into this topic, I'd like to talk on the Professor Walter Craig. Okay, I began to study the water wave problem around 1993. And at that time, I was a master course student, and I led this Walter's paper. This is my favorite Walter's paper. This paper was published in 1985 from Communications in Partial Differential Equations. And this paper is more than 200 pages, and this is printed in the old style typesetting, like this. Also, around this time, in 1985, the Japanese mathematicians, Professor Kano and Professor Nishida, also worked on the KDB approximation of the water wave problem from mathematical point of view. But as you know, this paper, this Walter's paper, is a first paper that gives mathematically rigorous justification of the KDB approximation of the water wave problem as an approximation of the solutions. So, and I was impressed, at the time I was impressed by this paper, Walter's paper. And since then, I'm working mainly the water wave problem. And at that time, and since then, for a long time, I did not know personally the Walter Craig. However, in 2016, I invited Walter to Japan at the occasion of the LIMS workshop on mathematical analysis in fluid and gas dynamics, held at LIMS at Kyoto University. Fortunately, Walter has not yet scheduled around that period, and he kindly accepted my invitation. And so he came to Japan with his wife, the other, and he talked on normal forms for water waves in this LIMS workshop. Here, this is the title of his talk in this workshop. And the Kyoto is one of the famous touristic place in Japan. So after finishing this workshop, we went sightseeing around this Kyoto area. And also he gave a talk on vortex filament dynamics in our nonlinear analysis seminar at Keio University. I'm also working on the vortex filament with ends at a little bit with my former student Aiki. So these topics are very interesting to me. And I also invited Walter to a dinner in my home in that occasion. Here, this is a picture at that time. Here you see the Walter and his wife, Diador, and my wife, Madoka, and me. So at the time, we have very much enjoyed spending the good time. And in the next year, 2017, it was my sabbatical year, and I was visiting Université de Bordeaux in France. And at the time, by coincidence, the Walter was also visiting the Université de Bordeaux with his wife, Diador, for several weeks. And at the time, the Walter proposed to discuss with David Lang at Bordeaux and me on a scattering problem for linear two-dimensional water waves with localized bottom topography, namely the scattering problem of the water waves due to the localized bottom topography. And by taking that opportunity, Walter, his wife Diador, my wife Madoka, and me, we went to nice restaurants in Bordeaux. And we have again very much enjoyed spending a good time. In fact, at some restaurant in a dinner, we went there when it opened, and we stayed there until when it closed. So at the time, Walter said, yeah, this indicates that we have enjoyed very much in talking. So here, this is a picture at a restaurant in Bordeaux. Yeah, Walter and me. So for me, Walter was very nice and a very kind person. And of course, he's a very good mathematician. Okay, now let's go back to mathematics. And let me formulate the water wave problem. And also let me explain the derivation of the Isobe-Kakinuma model and its basic properties, because the Isobe-Kakinuma model is not so familiar. So now we consider the motion of the water in n+1 dimensional space. And we assume the shape of the water region is like this. Here, this is the water surface denoted by a gamma of t. T is the time. And this blue region represents the water, and this region denoted by omega of t. And here, this is the bottom of water denoted by sigma. And we denote x as horizontal spatial coordinates and z as the vertical spatial coordinate. And we take the gravity into account as an external force, and g is the gravitational constant. And the surface tension, the effect of the surface tension on the water surface is neglected as usual. And moreover, we assume this water surface and this bottom are represented as graphs like this. Here, the eta represents the surface elevation, and this is one of the main unknown function. And the h, which is a positive constant, this is the mean depth of the water. And b represents the bottom topography, and this is a given function. And we are now considering the water waves. So we assume the water is an incompressible ideal fluid, and the flow is irrotational, as in the usual way. And then the fluid motion is described by the following equations. Here, capital phi, I use this notation. Capital phi is the velocity potential. And this Laplace's equation is a continuity equation in the fluid region, omega of t. And here, this is so-called Bernoulli's equation on the water surface. And here, this is a kinematic boundary condition on the water surface. Whereas here, this is a Neumann boundary condition, and this is a kinematic boundary condition on the bottom. And here, and in fact follows, we use the standard notation nabla as a nabla with respect to the horizontal spatial variables, and the nabla with suffix capital X as a nabla with respect to the whole spatial variables. And the similar notation will be used in the following, like this. This is a Laplacian in the whole space variables. Okay, as you know, nowadays water wave problem becomes famous. So as you know, these are the basic equations for water waves, and this is a starting point of our argument. So now we put phi as a trace of the velocity potential, capital phi, on the water surface. And then the basic, as is well known, the basic equations for water waves can be transformed equivalently into these system of equations for the surface elevation eta and this phi. This is, we have capital lambda. This is the Dirichlet to Neumann map associated with Laplace's equations. So as you know, this formulation is known as the Zakharov formulation or the Zakharov-Craig-Sulem formulation for water wave problem. Okay, now let me explain the variational structure of the water wave problem. In 1967, Luke showed that the water wave problem has a variational structure. And his Lagrangian density is given by this formula. The vertical integral in the water region to these quantities, the time derivative of the velocity potential plus half of the square of the velocity plus half of the gravitational constant g times square of the surface elevation eta. And this term corresponds to the kinetic energy of the water. And this term corresponds to the potential energy due to the gravity. And the action function is a space and time integral of this Lagrangian density. In fact, corresponding Euler-Lagrange equation to this Lagrangian is exactly the same as the basic equations for water waves. And Professor Isobe and Professor Kakinuma used this variational structure to derive their model. More precisely, in 1994, Professor Isobe proposed a model for water waves by approximating the velocity potential, capital phi, in this Luke's Lagrangian. This is a Luke's Lagrangian as follows. So he approximated this velocity potential like this, where capital phi I, this is an appropriate function system of the vertical coordinate z, and this may depend on the bottom topography B. So in this approximation, we have to specify this function system appropriately. Whereas here, this coefficient phi I are unknown functions. So now, plugging this approximation into this Lux Lagrangian, then we can obtain an approximate Lagrangian for these unknowns, the surface elevation eta, and this coefficient function phi 0, phi 1, blah, 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 phi capital N. And okay, their model is a corresponding Euler-Lagrange equation for this approximate Lagrangian. And 2000, Professor Kakinuma extended these techniques, this method, to the case of internal waves. So now we are considering the surface waves, but he extended this method to the case of internal waves. And since then, Professor Kakinuma, he gave many numerical simulations by using their model. Okay, but now different choice of this function system gives different Isobe-Kakinuma model. So which one is, so we have to carefully choose this function system in order to obtain a good model for water waves. So one of natural choices of that function system is as follows. Let P0, P1, blah, 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 P capital N be integers satisfying this ordering. And here, P0 should be 0. And we approximate the velocity potential capital phi by like this. So we take the base function Psi as the polynomial in the vertical coordinate Z. So we note that these polynomials are 0 on the bottom, except the case when I equal to 0. So this means that phi 0, in some sense, phi 0 denote the trace of the velocity potential on the bottom in the approximate sense. And here, these indices pi, practically, we choose pi as 2 times I in the case of the flat bottom, and I in the general case. So these choices are consistent with the Taylor approximation of the velocity potential for the full waterway problem around the bottom. Okay, now plugging this approximation into Lux Lagrangian here, then we obtain the approximate Lagrangian. And so this expression is very explicit, so we can write down explicitly this approximate Lagrangian. This is expression of the approximate Lagrangian, but a little bit complicated. But for the moment, this explicit expression is not so important. So just I showed that we can calculate explicitly like this. But here, just please memorize that we use this notation capital H, which is the water depths at point X at time t. So now it is not difficult to calculate the corresponding Euler-Lagrange equations. which are as follows. So these are corresponding Euler-Lagrange equations. And I think that these equations are a little bit complicated. So I think I have to explain these equations. So as a first variation with respect to the unknown function phi I to our approximate Lagrangian, we obtain this first equation. The time derivative appear only here. So this is an evolution equation for the surface elevation eta. And it contains up to the second order spatial derivative of phi j, and the derivative and the derivative up to the first order spatial derivative of eta. And here the indices I move from 0 to capital N. So this means that we have capital N plus 1 evolution equation for surface elevation eta. And now, as a first variation with respect to the surface elevation eta to our approximate Lagrangian, we obtain this second equation. The time derivative appear only here in the second equation. So we have just one scalar evolution equation for many unknown function phi I. And this contains the first order spatial derivative phi j of phi j, and does not contain any derivatives of eta, surface elevation eta. Okay, this is the Isobe-Kakinuma model in our choice of the base function. So therefore, we have so many evolution equations for just one unknown scalar function eta, and we have only one evolution equation for many unknown functions phi 0, phi 1, blah blah blah, phi capital N. So therefore, the Isobe-Kakinuma model is an overdetermined and underdetermined composite system. But anyway, the total number of equations are equal to the total number of unknown function. And in the following, we consider the initial value problem to this Isobe-Kakinuma model under these initial conditions. Okay. Now, let me explain the basic property of the Isobe-Kakinuma model. Before that, let me remind you that it is well known that the full water wave problem has three conservative quantities: mass, which is defined by this; the momentum in the horizontal direction, which is defined by this in the case of the flat bottom; and the total energy, the kinetic energy plus the potential energy. And here, this volume integral, we can rewrite this volume integral into the surface integral on the water surface, like this. And here, phi is a trace of the velocity potential on the water surface. And we can also rewrite this volume integral as a surface integral on the water surface, like this. Here, capital lambda is directly to Neumann map associated with Laplace's equation. So we have these conservation laws for full water wave problem. Okay, now Isobe-Kakinuma model has also three conservative quantities. The first is mass, which is the same; the momentum, which is defined by this in the case of the flat bottom; and the total energy, the kinetic energy and potential energy. And in order to define the momentum and energy, we have just replaced capital phi with our approximation of the velocity potential. And this volume integral, again, can be written in the surface integral like this. And here, this quantities is the trace of the velocity, the trace of our approximate velocity potential on the water surface. And we can also write this volume integral as a surface integral, but the expression is a little bit complicated, so I omit it. So the Isobe-Kakinuma model keeps these conservation laws. So the Isobe-Kakinuma model is not so bad, but however, Isobe-Kakinuma model has a serious drawback, as we can easily see as follows. The Isobe-Kakinuma model can be written in the matrix form like this. And we have the time derivative only here. Therefore, if the capital N is greater than 0, then this coefficient matrix has always 0 eigenvalue. So the hypersurface T equals 0 is characteristic for this model. So therefore, the initial value problem to the Isobe-Kakinuma model cannot be solved in general, even if the initial data is sufficiently smooth and small. In fact, we have capital N plus 1 evolution equation for just one scalar unknown function, eta. So by eliminating the time derivative of the surface elevation eta, we obtain this relation, which does not contain any time derivative. So in order to, as a necessary condition for the existence of the solution to the initial value problem, the initial data have to satisfy these conditions. So these are the necessary conditions. So now the problem is, if the initial data satisfy this condition, can we construct the solution of the initial value problem to the Isobe-Kakinuma model? The answer is yes, and more precisely, we have the following result. And more precisely, concerning the well-posedness of the initial value problem to the Isobe-Kakinuma model, we have the following result. With my former student, Murakami, in 2015, in a special case, and Nemoto, he's also my former student, in 2018, for the general case, we proved that the initial value problem to the Isobe-Kakinuma model were posed locally in time in the standard class. If the bottom topography satisfies this regularity and the initial data satisfy the previous necessary conditions, the sign condition, as in the case of the full waterway problem, the corresponding regularity to these function spaces, and the positivity of the water depths. So again, the Isobe-Kakinuma model is not so bad. But here we have some problem, one problem. Although the initial value problem is all well posed, how do we prepare the initial data for the variable of Isobe-Kakinuma model? Eta is a surface elevation, so this has a physical meaning, so it is not so difficult to specify the initial data for eta. And phi 0 is also have some physical meaning, but the other unknowns are just the coefficient. So how do we prepare the initial data of these variables which satisfy the necessary condition 7? The answer is as follows. I guess that nobody has any objection to impose the initial conditions on Zakharov's canonical variables, namely the surface elevation eta and this phi, the trace of the velocity potential on the water surface. So, okay, in terms of our variable to the Isobe-Kakinuma model, this quantity should be related by this relation. So phi should be defined by this, which is nothing but the trace of our approximate velocity potential on the water surface. And then we have the following proposition, which says that if the initial data of the Zakharov canonical variable eta and this phi, the trace of the velocity potential on the water surface, and the bottom topography B satisfy these irregularities and the positivity of the water depths, then the necessary conditions, and here this relation determine uniquely the initial data for the Isobe-Kakinuma model, which satisfy this estimate. So by using this proposition, once we obtain the initial data for the canonical variable, then we can construct the initial data for the Isobe-Kakinuma model. So again, Isobe-Kakinuma model is not so bad. So now, let's consider the Hamiltonian structure for the water wave problem. This is the main topic in this talk. And as you know, in 1968, Zakharov found a Hamiltonian structure of the water wave problem. And the Hamiltonian is total energy, the kinetic energy and the potential energy. And as I explained before, the canonical variable is the surface elevation eta and phi, the trace of the velocity potential on the water surface. And this total energy can be written in terms of these canonical variables like this, where capital lambda is a Dirichlet to Neumann map associated with Laplace's equation. So now, how about the Isobe-Kakinuma model? So as I mentioned before, the Isobe-Kakinuma model has the total energy of the Isobe-Kakinuma model is conserved. So this is the conserved quantities. So by the analogy of the classical mechanics, if the Isobe-Kakinuma model would have a Hamiltonian structure, then the Hamiltonian would be this total energy. Therefore, as I explained before, I remind you that this approximate velocity potential was defined by this. So, okay, it is maybe the Hamiltonian, but the problem is, which one is a canonical variable? What is a canonical variable? So we have many unknown functions, not only eta, but also phi 0, phi 1, blah, 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 phi capital N. So which one is the correct variable, and what is the complex structure? But again, the answer is finally, again, is very simple. The canonical variable is similar to the Zakharov's canonical variable, namely the surface elevation eta and this function phi, which is a trace of our approximate velocity potential on the water surface. These two variables are canonical variable. In fact, given this canonical variable, by the proposition 1, the necessary condition and this relation determine uniquely the variable of the Isobe-Kakinuma model, phi 0, phi 1, blah, 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 phi capital N. Now, this is denoted by this. So now plugging this into the total energy to the Isobe-Kakinuma model, we can express this total energy in terms of these two variables. And in fact, this is Hamiltonian of the Isobe-Kakinuma model. In fact, we have the following theorem. This is one of the main results in this talk. So the Isobe-Kakinuma model is equivalent to this Hamilton's canonical form, as long as these canonical variables have this regularity and the water depth is strictly positive. So, okay, this has a Hamiltonian structure. So now let's consider the relation between this Hamiltonian of the Isobe-Kakinuma model and the Zakharov's Hamiltonian. To this end, in the following, according to the bottom topography, we restrict the choice of the approximation of the velocity potential as follows. Namely, in the case of the flat bottom, we used we use only the polynomial of even degree, and in the general case, we should also use the polynomial of odd degree. But in this case, we have to add up to 2 times capital N. This means that in this case, the number of unknowns becomes nearly twice. And we consider the corresponding Isobe-Kakinuma model. And to this end, we rewrite all of the equations in a non-dimensional form. Let H be the mean depth of the water as before. Let lambda to the typical wavelength of the surface wave. And we introduce a non-dimensional parameter delta as a ratio of the mean depth to the wavelength, which represents the shallowness of the water. And we say that the water is shallow when this delta is small. And we descale independent and the dependent variables as follows. Then we can rewrite all of the equations in the non-dimensional form. And then we have the following theorem. This is the second main result in this talk. So which says that under appropriate regularity of the water surface and the bottom and the positivity of the water depths, the Zakharov's Hamiltonian in a non-dimensional form can be approximated by the Hamiltonian of the Isobe-Kakinuma model in the non-dimensional form up to of order delta to the power 4 times capital N plus 2. In a sense, this is very high. So the Isobe-Kakinuma model, the Hamiltonian of the Isobe-Kakinuma model is actually the higher order shallow water approximation of the Zakharov's Hamiltonian. And in fact, we have more rigorous result concerned to the shallow water approximation. Under appropriate assumptions initial data, the solution of the full water wave problem can be approximated by the solution of the Isobe-Kakinuma model in the non-dimensional form with an error of order delta to the power for capital N plus 2. This is the same order as before for some time interval independent of delta. So here I'd like to mention that in the case of the shallow water equations, this error is of order delta square. And in the case of the Grignard equations, Grignard's equations is known as higher order shallow water approximation. And in this case, the error is of order delta to the power 4. But even in the simple case, for example, capital N is equal to 1, then this order is of delta to the power 6, much better than the Grignard equation. So So I'd like to say that the Isobe-Kakinuma model is actually the higher order shallow water approximation. So this is the end of my talk. Thank you very much for your kind attention.